Hey there, so this is a video on volume. This is section 11.3. This would be like the second day. We spent a whole class period doing this section. So volume is just the space inside of a 3D figure or object. It does say closed. Technically the definition is a closed 3D figure of object, but there's plenty of figures like or objects like maybe a swimming pool, for example, that's, you know, it's not necessarily closed, but we find volumes of swimming pools all the time to figure out how much water is inside. So this is I would say the technical definition, but there are plenty of real life applications that kind of, you know, I would say extend this just a little bit. So our units for volume, we talked about this in 11.1, are all cubed. So these are cubed units. So units like cubic feet, cubic inches, cubic meters, etc. So before we start using volume formulas, what we're going to do is we're going to talk about non-standard units of volume, just like we did with area and surface area. So let's look at this example. This is screenshotted from your textbook, so you'll see this example in your notes, and or not in your notes, you will see it in your notes, but your homework too. And basically what this problem asks you to do is use these two units. You're going to do one at a time. So where it says cubic unit 1, let's just look at this small cube, and you're going to ask yourself how many of these fit inside this prism, or how many of those fit inside this prism over here. So let's do this first prism, and this would be a good time to pause the video and see if you could do this on your own, and then double check using the video. So I count, there are 8 of these on the top and 8 on the bottom, so it looks like there are 16 small cubes that fit inside of this larger prism on the left, and it looks like there are 8 on the right. So this next one, okay, we're going to do a new problem. So we're going to use cubic unit 2, which is this larger cube that has 8 smaller cubes in it. So it's got a volume of 8 smaller cubes. So one way to do this is you could visualize. So you could look and see, okay, well, I could probably fit one of those here and two and another one there. So there are 2 of those larger cubes that fit inside of this figure. Another way to think of it is if this larger cube here has a volume of 8 smaller cubes, if this figure has 16 smaller cubes in it, well, how many 8s go into 16? Well, there are 2 8s that go into 16, so there are 2, the volume is considered 2. So this next figure here, if we look at the prism on the right hand side, now it's not possible in this one to visualize how many of these cubes would fit in here because you can see they're different shapes. But we could think of this as 8 smaller cubes like we did in the last example and ask ourselves, okay, well, if this rectangular prism is 8 smaller cubes, how many of these, if this is 8 smaller cubes, fit into this one? Well, 8 times 1 is 8, so there are 1 of these that fit inside. So the volume would be 1 if our units are that cube number 2. Okay, so let's talk about some English units of volume. So we've got some really nice pictures here of what a cubic inch and a cubic foot and a cubic yard would look like. So this first one says how many cubic inches equals 1 cubic foot. So let's write down what we know about inches and feet. So we know there are 12 inches in 1 foot. If I want to know how many cubic inches are in a cubic foot, okay, then I need to cube both sides. 1 cubed, 1 times 1 times 1 is 1. Feet cubed is feet cubed. 12 cubed, 12 times 12 times 12 is 1,728 cubic inches. So that's how many cubic inches are in a cubic foot. You could also draw a picture for that too. Same thing with feet and yards. So this would be a great time, pause the video and try it. So there are 3 feet in 1 yard. And if I want to know the cubic conversion, I'm just going to cube both sides. 1 cubed is 1 cubic yard. 3 times 3 times 3 is 27 cubic feet. Okay, so it means there's 27 of these guys that fit into this larger one. And there's 1,728 of those little ones that fit into the middle one. And those aren't drawn to scale if you're wondering how that's possible, because it doesn't look like it in the picture. So this last example, how many cubic inches equals 1.4 cubic feet? So I'm going to write down 1.4 cubic feet, write it as a fraction, and I'm going to multiply. I'm going to use dimensional analysis, and dimensional analysis tells us that if we want to get rid of a unit like cubic feet, I'm going to put it on the diagonal so that they cancel out. And if I want cubic inches, that's what I'm being asked about, I'm going to put that on the top. And I know this conversion. I know we just figured it out in the first box. So for every 1 cubic foot, there's 1,728 cubic inches. And so at this point, we just multiply fractions. So the top times the top will give you the answer. And if you multiply those two numbers out, you get 2,419.2 cubic inches as the answer. Okay, so let's kind of transition to metric units. So this will be similar in how we approach it, but the nice thing about metric units is that the conversion is so much easier. And if you want, we can write down our King Henry died by drinking chocolate milk. Okay, if we want to do our metric converter, that might help. Remember that this B stands for base, which is meter. So the meter is in the middle. That's kind of like your 1, okay? And when you go to the right, so a decimeter is 1/10 of a meter, a centimeter is 1/100th of a meter, and a millimeter is 1/1000th of a meter. A decameter is 10 times as big, hectometer is 100 times as big, and a kilometer is 1,000 times as big. So we add a 0 or divide by a 0 depending on which direction we go. So if we want to know how many cubic centimeters equal 1 cubic meter, okay, one way to do that is we could write out the conversion between centimeters and meters, and we know there are 100 centimeters in 1 meter, and we could cube both sides just like we did in the last example. So 100 cubed, we're basically taking these two zeros and doing them 3 times. So we get 1, 2, 3, 4, 5, 6 zeros, which gives us 1,000,000 cubic centimeters in 1 cubic meter. Okay, so that's one way to do it. You could also use use the metric converter and start out at 1 meter, which is right here. And if we want to get to cubic centimeters, we're going to jump. But every time we jump, we're moving by a factor of 3. So it means 3, 6. We're moving 6 to the right. Or so we could write 1 cubic meter and move our decimal 1, 2, 3, 4, 5, 6. And we get 1,000,000 that way. So feel free to do it either way. For the second one, how many cubic millimeters equal 1 cubic centimeter? So you could say, you could put your pencil on centimeters. So let me see if I can erase this there. I'll just draw the line again. So if you could, let me identify, okay, so here's the centimeter. And if I wanted to go to millimeters, then I'm going to go to the right and I'm going to move my decimal 3 times, okay? So I'm going to write the number 1 and I'm going to move it 1, 2, 3 to the right, and I end up getting 1,000 cubic millimeters. Okay, and so for this last one, 3.4 cubic centimeters, I'm going to write that out. Okay, and I want cubic millimeters. So just like before, if I'm starting at centimeters and I want to convert to cubic millimeters, okay, so these right here, these are the linear measurements. Those are not cubic. So when I want to make a cubic conversion, cubic, think of 3, I'm moving the decimal 3 spots for every time I move on the metric converter. So going from centimeters to millimeters, I'm going to move my decimal 3 spots to the right. So 3.4, I've got 1, 2, 3, fill in with zeros. So 3,400 cubic millimeters is the equivalent conversion. Okay, so we're done with the conversions in terms of the notes, but there are a lot of examples in the book, and you can certainly do the, try more on the homework if you need more practice on those. So let's jump into the formulas. So let's look at the prism. So one thing that's going to be really important here is identifying what the shape is. So even though we did this in the previous chapter, you really need to be able to look at a figure like this and say to yourself, okay, what is this? It's a prism. Why is it a prism? Because it has two matching bases. The bases for a rectangular prism could be here and here. That's one option because those match. They could be here and here. That's another option. Or they could be the front and the back. Now with other figures, you don't have any option but one. So for example, on this triangular prism, the two matching bases are going to be the triangles. Okay, and the reason it's important to know what the bases are is because the volume of a prism, the formula is this big M means area of the base times the height. Now, one thing I want to notice, and this is really important, so define height. Okay, if you have a highlighter, you could highlight this part. You're going to ask yourself, how far apart are the bases, not how tall it is. So for example, on this triangular prism here, the height is actually going to be this distance right here because it's how far the bases are from each other. It's not how high it stands on the desk when it's sitting down, because you could orient this lots of different ways as it's standing. So in the second example, the bases would be here and here. So the height would be how tall it is, and same thing with this. You have a base on the top, base on the bottom. The height is going to be this distance. So let's jump into example 4. So the first thing I'm going to do is I'm just going to get in habit of writing down the formula. So I'm going to identify this is a prism. So I'm going to write down the formula, area of the base times the height. So the first thing I'm going to do is I'm going to find the area of the base. So in this case, the area of the base is a triangle. So I'm going to draw the triangle flat, and it looks like this triangle has a height of 3. I know because I see this right angle here with a base of 4. So the base is 4. So with area of the base, this you're going to have to use whatever formula you need to depending on what shape the base is. So if the base is a triangle, it's going to be 1/2 base times height of the triangle. So 1/2 times 4 times 3, and you're going to multiply that out, and we end up getting area of the base is 6 square centimeters. So that's one piece. The second piece is identifying the height. So if the bases are these triangles here on the ends, so if these are the bases, then the height is going to be the distance. How far apart are those from each other? So the height is going to be 10. So the second part is I'm going to do the volume. So volume equals area of the base times the height. So the area of base is 6, the height is 10. I multiply those together and I get a volume of 60 cubic centimeters. The second one, just like I mentioned before, with prisms, with rectangular prisms, you have some options. So you can make any of the matching sides bases, and no matter what way you do it, you should get the right answer. But keep in mind that let's say I make the top and the bottom the bases. The height is going to be how far apart they are, so the height is going to be 10. If I decided to make the bases like the front and the back, for instance, the height would end up being 15. So the height will change depending on which two parts you consider to be the base. So part 1, I'm going to find the area of the base, and the area of a rectangle, okay, is length times width. So if I'm looking at this rectangle right here, it looks like it is 10 by 15. So I'm just going to do 10 times 15, which gives me 150 for the base. Okay. Next, I'm going to come over and I'm going to do the volume. So volume equals area of the base times the height. So the area of the base is 150 times the height of the figure, which we said was 10. So we're essentially just adding a 0 to 150, so 1500, and that's going to be in cubic centimeters. So let's talk about what this means. And I want you to just kind of visualize this. It'd be easier if we were in class and I could show you with my hands, but why are we taking the area of the base times the height? Imagine this triangular prism. If you find the area of this triangle and you multiply it by 10, it's like taking this triangle and adding it up many, many, many times until it fills up this whole figure. Or like this prism over here, the rectangular prism, imagine what the area of the bottoms. This is kind of like the area of a room, okay? The bottom of a room, like the carpeting. And if you were to take that area and add it up or multiply by 10, which is basically like repeated addition, until it filled up the room, it would be filling up that space, and that's why we're doing that multiplication to find the volume. So the same thing is going to be true for cylinder. We're going to take the area of the base times the height, but for the cylinder, we actually we know a formula for area of the base. So for a cylinder, the bases are the circles, and the area of a circle is pi r squared. So I actually like to think of the formulas as area base times height because it allows me to just not memorize these, but you could just substitute pi r squared times h and use this as a volume formula for cylinder and add that to your formula sheet. And again, height is always perpendicular to the base, so it's this measurement. And if the cylinder were to be laying on its side, for example, the height would be that distance. So it's not always vertical. So let's do this next example. So example 5, we're going to write down the formula. So pi r squared times h. Okay, if the diameter is 5, then that means the radius is 2.5. So I'm going to do for pi 3.1416, or you could use the pi button in your calculator, times the radius squared times the height of the cylinder, and we get 196.35, and it asks to round to the nearest tenths place, which is right here. So this 5 tells us to increase that to a 4, so 196.4 square centimeters. All right, so the volume of a pyramid is a little bit harder to see. If I was in class, I actually have a really nice cube that I can show you, and a triangular or a pyramid, a square pyramid that fits inside. And the cool thing is that you can actually fit, so if you take a cube, it actually divides evenly into 3 square pyramids of the exact same size. So if we know the volume for this cube is area of the base times the height, then one of the pyramids is just going to be 1/3 of that. So the formula for volume of a pyramid is 1/3 area of the base times the height. So let's do an example. So let me just scroll down here to example 6. So I'm going to write down my formula. So volume equals 1/3 area of the base times the height. Now the height is going to be last time we talked about the slant height. So that's this 15.9. That's the slant height, the height of that triangular side. The height of the pyramid is going to be how tall it is. So imagine a pole connecting the top of the tent all the way to the center, okay, forming a 90-degree angle to the floor, and that's going to be your height. So your height in this example is 15.7. So really what we need to do is we need to figure out, well, what is the area of that base? And the base, just use a different color here, is going to be just this triangle. Okay, and in the last example, this is the same example we did for surface area. It's the exact same picture, and I added this. We need to add to the notes, and I should have put this in here, but I forgot. So this is an equilateral triangular pyramid, which means that that's an equilateral triangle base. So I'm just going to draw a picture of the base as best I can here. And it looks like this is 8, this is 8, this is 8, because it's an equilateral triangle. And I'm going to try to find the area of this triangle. Now we did, in order to find the area of this triangle, I need to know the height. And I don't know what that is. So we found this in our surface area example, but I'll do it again here. If we know the height and we know that the base is 8, or I'm sorry, we don't know the height. We're going to try to find the height. So in order to find the height, instead of labeling this 8, I'm going to label it as 4 and 4, because then what it allows me to do is it allows me to just look at this triangle right here, which is a right triangle, and use the Pythagorean theorem. So on the side, I'm just going to do the Pythagorean theorem, which is a squared plus b squared equals c squared. 8 is the longest side of that triangle, so that goes here. The other side is 4. And then the other side is that h that I'm trying to find. So h squared plus 16 equals 64. I could subtract 16 from both sides, and I'm left with h squared equals 48. And then take the square root of both sides, and I'm left with h, is approximately equal to 6.928. And you might be asking, well, why did you round to 3 decimals? I just picked. Honestly, I think you'd be fine doing 6.9. You were not going to get the problem wrong in your homework if you did it like that, but I think that's enough decimals to have a good degree of accuracy. So now what I'm going to do is I'm going to come over here and I'm going to write down, I'm going to find the area of the triangle. So this was step 1. Step 2 is going to be to find the area of the base. So since the base is a triangle, that formula is 1/2 base of the triangle times the height of the triangle. So 1/2 the base of the triangle is going to be 8. And the height of the triangle I just found with the Pythagorean theorem is 6.928. Okay, if I multiply that together, the area of the base is approximately 27.712. Okay, so there we go. And then I'm kind of running out of room here. I'm going to come over here on the left-hand side. Step 3 is going to be to do the volume. So volume equals 1/3 area of the base times the height. So I'm going to do 1/3 times 27.712 times the height, which is 15.7, the height of the pyramid, not the triangular base, but the actual pyramid. And if we multiply that all together, we end up getting about 145 cubic centimeters. Okay. So with cone is really similar. So we can start by saying that it's 1/3 area of the base times the height. It's really similar to a pyramid, but with a cone, the area of the base is going to be a circle. So instead of big B, I'm just going to write down the area of a circle formula, which would be pi r squared times the h. So this part right here is just the area of the circle, and then 1/3 and h make it the same or very similar to the pyramid formula. So the key here is in surface area, we talked about this distance right here called the slant height. I'm not needing that with volume. With volume, I want to know how tall is this cone if I put, if I connected the top all the way to the base here. So let's just scroll down. And in example 7, for surface area, it was really helpful for me to have that 20 right here. That was my slant height, and that was really helpful. In this example with volume, I need to know the height. So I'm going to have to do a little bit of work here. So I'm going to do the Pythagorean theorem because I have a right triangle. So I know that this right here is 12 and 20. So I'm just going to write down the Pythagorean theorem formula. So 8 squared plus b squared equals c squared. One of the measurements is 12. Okay, that could be my A. The other side is h. And I have to put 20 by itself because this is the longest side, or the hypotenuse. It's across from the right angle. So I'm just going to multiply that all out. So 144 plus h squared equals 400. Take away 144 from both sides. So I get h squared equals 256. Take the square root of both sides, and I'm left with h equals 16. So yay, we finally get a nice answer for a change when we do the Pythagorean theorem. So the next step is just to use the volume formula. So 1/3 pi r squared h. So 1/3, 3.1416, times the radius, 12, times the height of the figure, which is 16. And if we multiply that, we get 2,412.7 cubic centimeters. So this next part is volume of a sphere, let me just go ahead and write down the formula and I'll talk about how we get it in a minute. So the volume of the sphere formula is 4/3 r cubed times pi. So, and I'm just going to go ahead and write that for example 8. So 4/3 r cubed times pi. And you might be wondering, or not, where that formula came from. I'll just talk through it real quick because it's an interesting explanation. If you have a cylinder, okay, so imagine a cylinder like in this picture, and imagine a sphere, so like a ball that fits perfectly in this cylinder. So it fills up the cylinder so that the top of the sphere is at the top of the cylinder. Archimedes discovered that the volume of the sphere is 2/3 of the volume of the cylinder that contains it. He could have easily found that out by water displacement, so maybe filling up the cylinder with water, putting the ball inside, and then measuring how much water escaped to figure out that there was a 2/3 volume relationship. So what we could do is we could prove this by basically identifying, well, what is the volume of the cylinder? So we know the volume of the cylinder is pi r squared times h. And we know that the ball is supposedly 2/3 of that volume. So pi r squared times h. Now, we don't have an h in the volume of the sphere formula, but we do have an r. And if you look at the height of the cylinder, well, the height of the cylinder is kind of like the diameter of the sphere. So if the diameter is 2 times the radius, okay, that would be the height. So 2r is equal to the height. So this is r, and 2r is going to be the height of the cylinder. So instead of height, I'm just going to write 2r. And then essentially what we have is we have an r squared and an r, give us an r cubed. If you combine the 2 times the 2/3, then that gives us the 4/3, and then the pi stays there. So that's how we get the 4/3 pi r cubed. And this is not something you're going to have to prove in the homework or on the test, but I just think it's kind of interesting to go through that. So that gives us our formula for our sphere. So I'm just going to basically, this is pretty simple, like surface area. It's just a plug and chug. So you plug in, for example, 8, the radius, and whoops, instead of pi, I'm just going to write down 3.1416. And if we work that all out, we get about 589. So we get 588.978. And just pay attention in the homework how they ask you to round. But it looks like that's our volume. All right, so that really concludes volume. If you have any questions, just let me know.